Hello student, good morning. I am Dr. Kumar Sinha, Professor of Chemistry. Today I am going to discuss bonding in metal carbonyls. Last class I have discussed limitation of crystal field theory. Now I am going to discuss bonding in metal carbonyl. Bonding in metal carbonyls. The homoleptic carbonyls are formed by most of the transition metals. What is actually homoleptic carbonyls? Already I have discussed. Again I am telling you, compounds containing carbonyl ligands only. Compounds containing carbonyl ligands are called homoleptic carbonyls. Homo means one. Homo means one. A homoleptic carbonyls means the same. Then here carbonyls are the only ligands. Carbonyls are the only ligands, only one type. Then compounds containing carbonyl ligands are called homoleptic carbonyls. The homoleptic carbonyls are formed by most of the transition metals. These carbonyls have simple, well-defined structures. Tetracarbonyl nickel 0. Tetracarbonyl nickel 0 is the best example. And other example I am telling you, here actually tetracarbonyl nickel 0. This is actually tetrahedral. This is a tetrahedral. Other example is pentacarbonyl iron 0. Pentacarbonyl iron 0. This is actually trigonal bipyramidal. Its geometry is trigonal bipyramidal. And tetracarbonyl nickel 0, its geometry is tetrahedral. And pentacarbonyl iron 0 is trigonal bipyramidal. And one more example, hexacarbonyl chromium 0 is octahedral. Means if 4 ligands carbonyls are attached with the metal, central metal ion, then this is the tetrahedral. And here this nickel has 0 oxidation state. 0 oxidation state. And here you should know carbonyl means CO. Carbonyl ligands also is neutral. It has no positive, no negative charge. Carbonyl ligand is neutral. Then here in tetracarbonyl nickel, oxidation state of nickel is 0. And in pentacarbonyl iron, here also iron has 0 oxidation state. And this hexacarbonyl chromium 0. Here also chromium has 0 oxidation. And hexacarbonyl means when 6 carbonyls are attached with the central metal ion, it is called hexacarbonyl chromium. Here central metal ion is chromium and its geometry is octahedral. Octa means 6. Correct? Then tetracarbonyl means its geometry is tetrahedral. Pentacarbonyl means its geometry is trigonal bipyramidal. And hexacarbonyl chromium 0, here its geometry is octahedral. This decacarbonyl dimanganese. Now here another example is there. Deca means 10. Deca carbonyl means 10 carbonyls are attached. Where it is attached? Then now it is attached with 2 manganese, dimanganese. And in this complex, manganese has zero oxidation state. Means in all carbonyl compounds, in all homoleptic carbonyls, oxidation state of central metal ion is 0. Then decacarbonyl dimanganese is made up of 2 square pyramidal MnCO whole 5 units. Okay, MnCO whole 5 units joined by Mn bond. Means 2 units, 2 MnCO5 are joined to each other. Then bonds are between Mn and Mn bond. Octacarbonyl dicobalt, another example. Octacarbonyl dicobalt. Here also cobalt has zero oxidation state. Then octacarbonyl. Octa means 6. Now here 6 carbonyls are joined with 2 dicobalt means 2 cobalt. Then cobalt also both are linked. Means cobalt CO whole 3. Again cobalt CO whole 3 means cobalt cobalt CO whole 3 carbonyl. Then both cobalts are joined by each other. Cobalt bond bridged by 2 CO groups. Okay. Then now I am telling the structure. A structure is very simple. Nickel CO whole 4 means tetracarbonyl nickel. Tetracarbonyls. Okay, nickel, zero oxidation state. Then its structure is very simple. Nickel is in the middle and 4 CO are attached with nickel in tetrahedral form. Now next is FeCO whole 5. FeCO whole 5 means pentacarbonyl iron. Then here again iron is Fe is in the middle and 5 carbonyls are joined to the ferrous, and its geometry is trigonal bipyramidal. Means 2 carbonyls are just like a straight line, just like one carbonyl is above Fe and other carbonyl is down straight way, and rest 3 are in a triangular form. One Fe is down and 2 are above. Means if you join these three CO and 2 is up, 1 is down. Means left and right. Left side 2 and right side 1. If you join, it will look like a triangle. That's why it is called trigonobipyramidal. Why you are telling? Because one CO is up, then it is making one pyramidal. But down is also one CO. Then that's why it is making 2 pyramidal. That's why name has been given trigonal bipyramidal. Now other structure I am telling you, cobalt 2 CO whole 8 octacarbonyl cobalt 0 complex. Here 8 carbonyls are there. Then 8 carbonyls are there. Then 4 carbonyls means CO are attached. 4 are attached with each cobalt. Correct? Means this each cobalt from one cobalt 4 ligands are attached. 4 CO are attached with the cobalt, one cobalt, and other you can say with other cobalt again 4 carbonyls are joined to each other. Okay, and both covalts are joined to each other. Means 4 carbonyls are joined with one cobalt, and other 4 carbonyls are joined with other cobalt, and again cobalt and cobalt, both cobalts are joined to each other. Okay, then here 3 cobalt will be one side, on each cobalt 3 will be, you can say, upside, and fourth one cobalt, fourth one carbonyl. 3 carbonyls of both cobalt are means 3 are left side and other 3 are right side, and both cobalts are joined, and fourth one carbonyls are fourth one carbonyls which is joined by cobalt only, but they are for each cobalt, or you can say from each cobalt fourth one carbonyls are joined. Then both carbonyls are crossing to each other in the down. In the down, fourth carbonyl means carbonyl of first cobalt and carbonyl of second. They are crossing. In the down. Okay. Then this I told you a structure of cobalt to carbonyl 8 CO whole 8. Okay. And this I told about the cobalt, and now I am telling you a structure of chromium CO whole 6. Chromium CO whole 6. Okay, octahedral. Then here what you will see in this structure, all 6 are joined with carbonyl. All 6 are joined with carbonyl. Correct? And it is just like a circle. It will look like a circle. Okay. That 6 carbonyls are surrounding this chromate, chromium. All are joining with chromium. It is just like a circle. All 6. And its structure is octahedral. And its common structure is octahedral. Like that way now, Mn to cobalt 10 means Deka. Okay. That Mn, I told you, Deka-carbonyl dimanganese. Deka-carbonyl dimanganese means now 2 manganese are there and total 10 carbonyls are there, CO. Then from each Mn 5 are joined. Okay, 5 carbonyls are joined from each Mn, and both Mn are joined to each other. Okay, means it is a bridge. Mn are joining to each other, and each carbon from each manganese, both manganese are joined to each other, and from each manganese 5 carbonyls are joined. Okay, 2 upside, 3 down. Same way with second manganese also, 3 are upside, 2 are down. Means you can understand like that, very simple way, that manganese, 2 manganese are joined to each other in a straight way, just like 180 degree, and only in 180 degree, that side, right side, 1 CO is attached, and left side with other Mn, 1 CO is attached. Correct? And then I told about the 2 CO in a straight line. Now again 2 CO with first Mn. First Mn, 2 COs are just like a perpendicular. One is up, other is down. Correct? Just like a perpendicular. In a straight line from up to down. One CO is upside, other is down. Same way with second Mn, one CO is up, other CO is down, straight way. One above the Mn, other below the Mn. Then now I told you about the, you can say this 2 to 4 to 6 carbonyl I told you. Now rest 4 are there. Then now on each Mn 2 are again there. They are also just like a straight only. Straight CO and CO through Mn both are attached. Here also both CO through Mn it is attached, but these two CO Mn of you can say Mn of both CO of Mn, both carbonyl of Mn, and both carbonyl of second Mn, both are parallel. Okay, parallel. Correct? First Mn 2CO and second Mn 2CO are parallel. One is down, other is up. Then you can tell that now 4 orbitals are 4 ligands are parallel. 4 ligands are parallel. Okay, that is in first Mn 2 ligands, which is you can say one up and one down. That is parallel with second Mn. There also one CO is up, other CO is down. Both are parallel. And this again two more CO of first and two CO of second Mn. Again both are parallel. Correct? And in the beginning I told you that just Mn have joined to each other, and each Mn only in the same direction, it's 180 degree. That is with one Mn one CO is there, and with other Mn one CO is there. Then now on each Mn 5 ligands are there, means carbonyls are there, total 10. That's why it is called Deka-carbonyl dimanganese. Manganese has 0 oxidation state. Okay. Now one more bonding I am telling you, that is called synergic bonding. Synergic, SYNERGIC, synergic bonding. Question is asked. Okay, here the metal carbon bond in metal carbonyls possesses both. First, a little I will tell about this complexes what I discussed. Carbonyls, metal carbon. Metal means here manganese, iron, nickel. These are the central metal ion. The metal carbon bond, because carbon is joined on a carbonyl, carbon is there, CO, that carbon is joining with metal like manganese, like Fe, like nickel, like chromium. Okay, the metal carbon bond in metal carbonyls possesses both S and P character. Okay, this is important. The metal carbon bond in metal carbonyls possesses both S and P character. The metal carbon sigma bond is formed. The metal carbon sigma bond is formed by donation of lone pair of electrons on the carbonyl cation into vacant orbital of the metal. That you know, carbonyl has lone pair of electron. That electron will be this carbonyl will donate the electron pair to the d orbitals of central metal ion like normal way in complex formation. Okay, the MC sigma bond is formed by donation of lone pair of electrons on the carbonyl carbon into vacant orbitals of the metal means d orbital. In metal d orbitals are there, vacant d orbitals. There carbonyl will donate the lone pair of electron. Now pi bond, come to the pi bond. The MC bond, bond between M and C, pi bond, they are making sigma bond also, pi bond also. Then bond between M and C, that is MC pi bond, is formed by the donation of a pair of electrons from a filled d orbitals of metal into vacant anti-bonding orbitals of carbon monoxide. Now reverse case, in a reverse way. Okay, for pi bond, how they are making pi bond? Then pi bond is formed by the donation of a pair of electrons from filled d orbitals. In d orbitals, some orbitals may be having lone pair of electron, means filled d orbitals. That in metal d orbitals, filled you can say electrons from filled d orbitals. That metal will donate now electron to where? Vacant anti-bonding orbital of carbon monoxide. Now metal is donating electrons. Metal d we can say d orbitals of metal. They may have. Okay, in carbonyl case, certainly that d orbitals will have, you can say, this filled d electrons. Filled electrons will be there. Then filled d orbitals of metal, electrons from a filled d orbitals metals. Filled d orbitals, electrons from a filled d orbitals of metal into the vacant anti-bonding orbitals of carbon monoxide, and it will form pi bond. The metal to ligand bonding creates a synergic effect. Correct? Then that is the synergic, means here two bonds are there, one pi bond, one sigma bond, other is pi bond. Then to make the pi bond, electrons are donated from a metal to carbonyl and anti-bonding orbitals of carbonyl monoxide. Then here the metal to ligand bonding creates a synergic effect which strengthens the bond between carbonyl and metal. Okay, that's why carbonyls, that bonding in metal carbonyls has importance due to this reason, because in general bonding in complex ion, only one-sided was there, means ligand were donating electrons to the metal, means vacant d orbitals of metal, ligand were donating. Okay, but in this case metal one that will be there, that is as usual what was going on, that will be going on, means CO will donate lone pair of electron the vacant d orbitals of metal ion, as usual it will give. But extra thing is here, that the electrons from the metal d orbitals of the metal, that will donate electron to the carbonyl. Okay, and this is actually called bond form is called synergic bond, or bonding is called synergic bonding. Okay, the metal to ligand bonding creates a synergic effect which strengthens. Benefit is that because now it is a double bond. Okay, then due to this synergic effect which strengthens the bond between carbonyl and the metal. Okay, then this I told about the synergic bonding. Then in carbonyl bonding, two types of bonds are there. One is pi bond, other is sigma bond. Okay, then this I discussed the distance now bonding in metal carbonyls. Now I am going to discuss stability of coordination compounds. Stability of coordination compounds. This is also very important. Question is asked. The stability of a complex in solution refer to the degree of association between the two species involved in the state of equilibrium. Again you listen. The stability of a complex in solution refers to the degree of association between the two species involved in the state of equilibrium. Two species involved in the state of equilibrium. The magnitude of the stability or formation, you can tell. The magnitude of the equilibrium constant. How much, what is the, you can say, magnitude of the equilibrium constant for the association quantitatively expresses the stability. Okay. Again you listen. The magnitude, how much actually, the magnitude of the equilibrium constant for the association quantitatively expresses the stability. Okay. Sorry for interruption. I was discussing about the stability. The stability of a complex in solution refers to the degree of association. Degree of association between the two species involved in the state of equilibrium. The magnitude of the equilibrium constant for the association quantitatively expresses the stability. Thus, if we have reaction, suppose metal plus 4 ligand, L means ligand, capital M plus 4L, then it will form Ml4, means complex it will form Ml4. Then both will be in equilibrium. 4 plus M plus 4L, it is forming Ml4. Then there will be equilibrium. M plus 4L, it is the reactant and it is giving product Ml4. Then these both will be in equilibrium. Means Ml4 again it can give back to M plus 4L. Okay. That's why both are in equilibrium. Then in this situation, in this type of reaction, larger the distance for this type of reaction, larger the stability constant, the higher the proportion of Ml4 that exists in solution. Means if in the equilibrium Ml4 is more, means formation is more, larger the stability constant, the higher the proportion of Ml4 that exists in solution. Means if Ml4 is more, complex is more formed, already formed more, then it means it is stable. Free metal ions rarely exist in the solution. Free metal ions rarely means no, you can tell. Free metal ions rarely exist in the solution, so that M will usually be surrounded by solvent molecules, which will complete the ligand molecules L and be successively replaced by them. Okay, here you have to understand that free electrons, free metal ions that rarely exist in the solution. First important point. And it will not exist in the rarely, I am telling you. Free metal ions rarely exist in the solution, so that M will usually be metal, M means metal, will usually be surrounded by solvent molecules. Solvent may be water, okay, which will compete with ligand molecules in the solution. Solvent may be also there, ligand may be also there. Then both will competition will be there. Who will reach to the metal? Okay, then this I am telling that free metal ions rarely exist in the solution, so that M will usually be surrounded by solvent molecules, which will compete with the ligand molecules L and be successively replaced by them. Means H2 ligand, the solvent molecules will go and L will come in its place. Just I am telling you example for simplicity. We generally ignore these solvent molecules. We will ignore only ligand, how it is coming, attaching, that I will tell you. Okay. Then here 4 stability constant we can tell, because 4 ligands are there. One by one it will attach with metal. Then for each step, what is the stability, equilibrium constant, that I will tell you. Then metal plus 1L, M plus L, M capital M means metal plus L, then it will form Ml. Then that time what will be the equilibrium constant value? Then equilibrium constant, you know, Ml, metal, this concentration of Ml means concentration of product divided by concentration of here M and concentration of L. In general way, equilibrium constant will be concentration of product divided by concentration of reactants. Then here molar concentration of Ml divided by molar concentration of M into molar concentration of L. Then its value is K1. You consider as a K1. Then K1 is equal to molar concentration of Ml divided by molar concentration of L into molar concentration of L. M and L. Molar concentration of Ml means product divided by molar concentration of M metal and into molar concentration of L means ligand. This is the K1 when one L joined. Now process will continue because 4 ligands are there. Now in Ml, one more L will join. Then now it will form Ml2. In this case, what is the K2? Then now K2 is equal to Ml2, molar concentration of Ml2 divided by molar concentration of Ml into molar concentration of L. Okay. Now like that way, if one more L will come, third, then now Ml2 plus L, it will form Ml3. Then now what is this equilibrium constant? In this case, K3 is equal to Ml3 molar concentration of Ml3 divided by molar concentration of Ml2 into molar concentration of L. Like that way, fourth one will join in this Ml3 plus L. Then now it will form Ml4. Then K4 is equal to, means equilibrium constant will be K4. Then K4 is equal to Ml4 divided by molar concentration of Ml3 into molar concentration of L. Correct? Then here K1, K2, etc. are referred to as a stepwise stability constant. Okay, K1, K2, K3, K4. These are referred to as or called stepwise stability constants. Okay, or directly you can write M plus 4L. It will give Ml4. Okay, but both will be in equilibrium. Then M plus 4L, it will give Ml4. And for this reaction, directly what is the equilibrium constant you can write? Suppose it is a beta 4. Then that is equal to molar concentration of Ml4 divided by molar concentration of M into molar concentration of L power 4. 4L was there, hence L power 4. The stepwise and overall stability constant are therefore related as beta 4 is equal to, beta is the suppose overall, then beta 4 is equal to K1 into K2 into K3 into K4. If 5 are there, then into K5. If 6 are there, 6 ligands are there, then into 5th into 6, like that way. Then overall is beta 4. If it is 6 ligand, then beta 6. If 5, then beta 5. Okay, that is over, beta is here, overall equilibrium constant. Correct? I have told you. Then this, suppose 4, 5 are there, 5 ligands are there or 6 ligands are there, then you can write beta is equal to, or beta n. You don't know how many ligands are there. Then beta n you can write. N. You don't know what is the value of n. Then beta n is equal to K1 into K2 into K3 into K4 into K5 dot up to Kn. Then beta n is equal to, you write, equal to K1 into K2 into K3 into K4 dot up to Kn. Now you take example. If we take as an example the stepwise involved in the formation of cupra ammonium ion means CuNH3. Then what will happen? Same way, Cu is 2 plus. Then Cu2 plus 1 ammonia, NH3, 1 ammonia. Then it will form CuNH3. And power will be 2 because an ammonia is neutral. Hence, charge will be 2 plus. What was the charge of oxidation state of copper? Only that will remain. Now, in this, you can say CuNH3. Suppose, but for this reaction step, first step, what will be the K1? K1 is equal to CuNH3, means concentration, molar concentration of CuNH3. CuNH3 divided by molar concentration of Cu2 plus into molar concentration of NH3. Like the same way, now in this reaction, again suppose in this complex CuNH3 whole to one more ammonia is adding. Now this time it will form CuNH3 whole 2 plus. Oxidation state will not change because ligand is neutral. Then in this step, K2 is equal to same way, molar concentration of CuNH3 2 plus divided by molar concentration of CuNH3 into molar concentration of again NH3, new NH3. Like that way, third, fourth can join. Then these K1, K2 are the stepwise stability constant. This equilibrium constant is called a stepwise stability constant. Overall overall equilibrium constant is called stability constant, and overall stability constant. Okay, stepwise stability constants. जैसे K1, K2, K1, K2, K3, Kr, these are the stepwise stability constant. Or if you want to tell only overall, then in that way it is called overall, like Bn, beta n, that is the overall stability constant. Then you can write beta 4 is equal to CuNH3 whole 4, 2 plus means now complex ion you write CuNH3 whole 4 in a square bracket, and outside 2 plus is there, and down you will write Cu2 plus and NH3 power 4. NH3 because 4 ligands are there, power 4. The addition of the 4 amine group to copper shows a pattern found for most formation constant. For other reaction also same way. That is called found to for most formation constant. In that the success stability, or you can tell successive stability constant, decreases. Here important thing is there that here the addition of the 4 amine groups to copper shows a pattern found for most formation constant. Okay, formation constant. In that the successive stability constant decreases. In the beginning it will be more. As the ligand will increase, then stability will decrease. Okay, that successive stability constant decreases. Okay, in this case the 4 constant value I am telling you, for the first one log K1, its value is 4.0. in this case. In the complex copper ammonium ion, in that I am telling you log K1 value is 4.0, and log K2 value is less, 3.2, and log K3 third value K3 is 2.7, decreasing, and log K4 is further decreased, 2.0. Okay, then if you will add all, then overall constant means stability constant will be 11.9. Just to add 4 plus 3.2, it becomes 7.2 and 2.7, then become 9.9, and 9.9 plus 2, 11.9. Then this is the overall stability. The instability constant, or the dissociation constant. Now I am talking about the dissociation. It was for association, formation, association. Now dissociation. Dissociation constant is also called instability constant. Reverse of stability constant. The instability constant, or the dissociation constant of coordination compound, is defined as the reciprocal of the formation constant. Question is asked. Okay, reciprocal of formation constant means 1 upon stability constant. 1 upon stability constant, that is reciprocal. Then instability constant, or the dissociation constant of coordination compound, is defined as the reciprocal of the formation constant. Now I am telling the importance of, now I am going to discuss importance and application of coordination compounds. This is again very important. Many question is asked, and in this many things you might be knowing also. Okay, because it is related to the complex compound. Then I am telling now importance and applications of coordination compounds. The coordination compounds are of great importance. These compounds are widely present in the mineral, plant, and animal worlds and are known to play many important functions in the area of analytical chemistry, metallurgical chemistry, biological system, industry, and in medicine. Okay, here applications are there. They play many important function in the area of analytical chemistry, metallurgy, biological system, industry, and medicine. In medicine also it plays a big role. Now I will tell you one by one. Coordination compounds. First, coordination compounds find use in many qualitative and quantitative chemical analysis. If you will go to the lab, then you will feel the importance. The familiar color reaction given by metal ions with a number of ligands, especially chelating ligands, as a result of formation of coordination complex from the basis for their this formation of colored solution I am talking about. Color of the reaction given by metal ions with a number of ligands, especially chelating ligands, as a result of formation of coordination entities, form the basis for their detection and estimation by classical and instrumental methods of analysis. Examples of such reagents include EDTA, it forms complex. EDTA forms complex. DMG, EDTA means ethylene diamine tetraacetic acid or acetate. DMG, dimethyl glyoxime, DMG, dimethyl glyoxime. Alpha nitro, third example, alpha nitro beta naphthol. Alpha nitro beta naphthol. And next is cupran. These are the complex molecules. Now second, I am talking about hardness of water. Hardness of water is estimated by simple titration with sodium EDTA. Sodium Na2-EDTA, ethylene diamine tetraacetate, its salt. Its salt is used in the determination of hardness of water. Hardness of water is estimated by simple titration with sodium EDTA. Here what will happen? The calcium and magnesium ion present in water. The calcium and magnesium ions present in water form stable complexes with EDTA. Its color will be, when calcium and magnesium will form complex with EDTA, its color will change. Okay. Then by that way you can find out that in water calcium and magnesium is there, and how much calcium and magnesium is there, then you can estimate it by use of formula. The selective estimation of these ions can be done due to difference in the stability constant. Difference in the stability constant of calcium and magnesium. How much this stability is there by its value. If stability is more, means calcium is more. If magnesium stability is more, it means magnesium is more. That constant value, stability constant value will tell about the estimation. Stability constant. Then by knowing the stability constant of calcium and magnesium complexes, we can estimate the hardness of water. Next application that I will discuss now, that some important extraction process of metals. Metal is extracted, then there it is used. Some important extraction process of metals like those of silver and gold make use of complex formation. Gold, for example, combined with cyanide in the presence of oxygen and water to form the coordination complex like AuCN whole 2 outside 1 minus. Then this complex it will form and its color will be different. Gold, for example, I am telling you, combines with cyanide in the presence of oxygen and water to form the coordination complex AuCN whole 2 outside 1 minus in aqueous solution. Gold can now complex form, and this from this complex auric means gold can be separated. Gold can be separated in metallic form from the solution by the addition of Zn. If we will add the Zn, then Au will be free and Zn will form this thing, ZnCN whole 2, it will form. Au will be free. Then in metal extraction, it is used. Means use of coordination is applicable in metal extraction. Now next application, I am telling you, similarly purification of metals. Purification of metals can be achieved through formation and subsequent decomposition of their coordination compounds. First compound will be formed and second compound will be decomposed, can be decomposed. Decomposition can be done. Okay, then you will get pure metals. Okay, purification of metals can be achieved through formation and subsequent decomposition of their coordination compounds. Example, impure nickel. Impure nickel is converted to nickel tetracarbonyl NiCO whole 4. Impure nickel is converted to NiCO whole 4, which is decomposed to yield pure nickel. Then see the application. Now next application I am telling you, coordination compounds are of great importance in biological system. Okay, biological system, it has importance. The pigment responsible for photosynthesis. Actually, in photosynthesis, green you have seen leaf, all leaves are green due to the photosynthesis. Then here pigment, chlorophyll, I am talking about green material. The pigment responsible for photosynthesis, that is the chlorophyll. Chlorophyll, what is this chlorophyll? Green material, this is pigment actually, coloring matter, chlorophyll. Then what is this chlorophyll? Then chlorophyll is a coordination compound of magnesium. This coloring matter, a green matter, is called pigment, responsible for photosynthesis, is a coordination compound of magnesium. Remember, question is asked. It is the coordination compound of magnesium. Now next example, hemoglobin. Hemoglobin, blood I am talking about. Hemoglobin, the red pigment of blood. Red, why blood appears red? Now you can understand the reason. Hemoglobin, the red pigment, hemoglobin is the pigment actually, red pigment of blood, which acts as a oxygen carrier. You know, blood carries the oxygen. It acts as a oxygen carrier. Hemoglobin is a coordination compound of iron. And due to this iron, blood looks red. Due to the presence of iron, formation of iron complex. Actually, hemoglobin is a coordination compound of iron and its color is red. That's why blood appears red due to presence of iron complex. Vitamin B12. Now next example, vitamin B12. Cyanocobalamine. The pernicious anemia factor. These are also coordination compound of cobalt. Again you listen. Vitamin B12 is a coordination compound of cobalt. cyanocobalamine, cyanocobalamine. Okay, here cobalt is there. And then I am talking about vitamin B12 has it is actually coordination compound of cobalt. Okay, and it functions as the anti-pernicious anemia factor. Then vitamin B12, cyanocobalamine, the anti-pernicious anemia factor, is a coordination compound of cobalt. Again, I am telling you, among the other compounds of biological importance with coordinated metals are the enzymes. All enzymes, almost all, will be complex compound. Okay, like carboxypeptidase, it is enzyme, ASE in the end. Carboxypeptidase. Carboxypeptidase is a enzyme and it is a complex compound. It is a complex molecule coordination compound. Okay, enzyme is a coordination compound. And this I told you enzyme. I give the example. That is example of coordination compound. And carbonic anhydrase. Another enzyme is carbonic anhydrase. This is the catalyst of. These are also biological catalyst. Carbonic anhydrase, it is enzyme. Other examples I told you, carboxypeptidase. Then all are coordination compound. Okay. Now next application I am telling you, coordination compounds are used as a catalyst for many industrial processes. You know well. Examples include rhodium, RH, rhodium complex. Rhodium complex means RH is the symbol for rhodium. Central metal ion is RH, means PH3P whole 3 RHCl. This is actually PH3P. PH means phenyl. 3 phenyl is attached with P. Once I told you PH3P means with just like a PH3 phosphine gas is there, PH3, then all 3 H went and its place 3 benzene came, 3 hydrogen gone and is substituted with 3 benzene means phenyl group. Okay, C6H5. Then it 3 molecules of this PH3. 3 molecules of PH3 means with the P3 PH3 is attached. Like this way 3 that will attach with rhodium and 1 chloride will be also attached. Then this is called rhodium complex. Then this is actually this is the actually catalyst. This is a catalyst. Then this coordination compounds used as a catalyst. Example I told you, rhodium complex. This is also known as Wilkinson catalyst. Okay, this is also known as Wilkinson catalyst. A Wilkinson catalyst is used for hydrogenation of alkenes. In means double bond is there. You want to I can say to add hydrogenation you want to do, then this catalyst is used, rhodium complex. Now another application I am telling you, articles can be electroplated. Electroplating I am talking about. Articles can be electroplated with silver and gold. If ordinary, suppose you have copper articles are there, and if you want to show it as a silver jewelry or gold jewelry, then what will you do? There it is used. This concept is used, coordination compound. Articles can be electroplated with silver and gold much more smoothly and evenly from solution of the complex AgCN2. That time for silver electroplating you will use the silver complex AgCN2 1 minus, And for gold electroplating, you want to make a gold look like gold, electroplating of gold, then it can be electroplated with gold. In that situation, AuCN whole to 1 minus is required. That is, a complex ion is required. Then gold complex is required for the gold electroplating, and silver complex is required for silver electroplating. Okay. Then this I have told used. Again, two more I will tell you. In black and white photography, now that nowadays it is also used in black and white photography. Now colored photography you are doing, but I am talking about in black and white photography. The developed film is fixed by washing with hypo solution. Hypo means sulfur. Hypo solution which dissolves the undecomposed silver bromide. Undecomposed. It is washed with hypo solution which dissolves. This hypo solution what will you do? Which dissolves the undecomposed silver bromide to form a complex AgS2O3 whole 2. AgS2 whole 3 AgS2 whole 3, not whole 3, AgS2O3 whole 2, AgS2O3 whole 2 power 3 minus. This is the complex of silver. Then in photography also this is used. Coordination compound is used. Okay, complex is used. Now one more I want to tell you. There is a growing interest in the use of chelat therapy. Cancer, cancer therapy will be there, chemotherapy. In that sense you can tell. There is a growing interest of use of chelat therapy in medicinal chemistry. An example is the treatment of problems caused by the presence of metals in toxic proportion in plant or animal system. If in plant metal is there creating problem, or in animals metal is there creating problem, their treatment. Then treatment of problems caused by the presence of metals in toxic proportion. Means it is that metal is creating, metal generally will be toxic, and that particularly transition metals will be generally toxic. Then this, if they are found in more quantity, then they will create problem. Then in their treatment, that metals in toxic proportion in plant or animal system, it is used. Excess of copper, suppose copper is there in plant, more copper is there or more iron is there. The excess of copper and iron are removed by the chelating ligands. What they will do? Chelating ligands will make a complex with copper and iron. Means copper and iron will behave as a central metal ion, and chelating agents you will use. Then it will form complex. Okay. Then excess of copper and iron are removed by chelating ligands. D-pencilamine and D-ferrioxime. D-pencilamine and this ferrioxime beta. Actually what they will do? D-pencilamine and this ferrioxime, ferrioxime beta, via the formation of coordination compounds. It forms coordination compound. Okay. Excess of copper and iron are removed by chelating ligands. And what it will form? Chelating ligands. This copper and iron are removed by chelating ligands. They will form D-pencilamine and D-ferrioxime beta via the formation of coordination compounds. Now EDTA, already told you, EDTA is used in the treatment of lead poisoning. If you want to remove the lead, then treatment EDTA can be used. It will also form complex with lead. Okay, EDTA is used in the treatment of lead poisoning. Some coordination compounds of platinum effectively inhibit the growth of tumors, means cancer. Okay, this some coordination compounds of platinum, platinum coordination compounds of platinum effectively inhibit, means stops or decreases, inhibits the growth of tumors. It will either cure, it will stop, or finally it will, at least it will inhibit, means it will decrease sometimes, sometimes it will stop completely the tumor. Tumor is in indirect way cancer. Examples are cisplatin. Cisplatin is the example. Okay, this is used. Cisplatins are used and its related compounds. Cisplatin and other compounds are used to remove to inhibit the growth of, they will stop or they will decrease the growth of tumors. Means in cancer treatment, cisplatin is used. Now I am stopping only here. I have finished complete this chapter, coordination compounds. I have completely finished, and your this full portion first part full portion I have finished. Okay, next class I will start, that is the part 2. That is organic chemistry. I will start in the next class. Thank you.